You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at https://www.computernetworkassignmenthelp.com. 1. Consider the following pseudocode snippet: address in hexadecimal, followed by pseudo-assembly code. 1000. Branch Conda 1018-1004. Branch Con B 1014-1008. Branch Con C 1014-100C. ADD 1010. MUL 1014. Branch Conde 1004-1018. Sub. A. Suppose we are using a share predictor with a history of length 2, just to keep the example simple. Suppose also that we have a 32 entry table of counters. Our share predictor hashes into this table by taking bits 6:2 of the current PC and XORing with the current 2-bit history. Construct two paths through the code, ending at different branch instructions, but that cause the predictor to hash to the same table entry. This is probably easier if you draw the code out as a flow graph. Clarification: history register left shifts, the older history bit gets XORed with PC 3, the newer history bit gets XORed with PC 2. 1000 1004 1008 100 C 1010 1014 1018. 1004 taken to 1014 taken to 1004 1000 not taken to 1004 not taken to 1008, both paths hash to table entry 2. computernetworkassignmenthelp.com. B. Construct two distinct legal paths through the code, both ending at the branch at address 1014, but that produce the same 2-bit global history. 1000 not taken to 1004, 1004 taken to 1014, 1004 not taken to 1008, 1008 taken to 1014. 2. You are designing the new ILN 511 processor, a 2-wide in-order pipeline that will run at 2 GHz. The pipeline front-end, address generation, fetch, decode, and in-order issue, is 14 cycles deep. Branch instructions then take 6 cycles to execute in the back end, load and floating point instructions take 8 cycles, and integer ALU operations take 4 cycles to execute. A. Your lab partner has written some excellent assembly code that would be able to achieve a sustained throughput on the ILN 511 of 4 billion instructions/second, as long as no branches mispredict. Assume that an average of 1 out of 10 instructions is a branch, and that branches are correctly predicted at a rate of p. Give an expression for the average sustained throughput in terms of p. Expected instructions to next mispredict ISE 10, 1p. Number of instruction slots, 2 slots/cycle. To execute all those and then get the next good path instruction to the issue unit ist E2 2010 40 50 40p. So the utilization rate at which we 1p 50 40p execute useful instructions, ISE/T10. computernetworkassignmenthelp.com. B. Unfortunately, it turns out that there was a bug in the original code. The bug fix made the code somewhat larger, and now you are observing instruction cache misses in the 2 kilobyte L1 instruction cache. Each L1 cache miss causes a 10-cycle bubble to be inserted in the instruction stream, while we fetch the cache line from the L2. If you could only double the size of the L1 cache, you could completely eliminate the L1 cache misses. Unfortunately, building a 4 kilobyte fully pipelined 2 GHz L1 cache would add an extra 5 cycles to the front end. Under what circumstances, e.g. cache miss rate and branch prediction rate, would it be a good or bad idea to change the pipeline to include the larger cache? If we increase the cache size, the branch mispredict penalty increases from 20 cycles to 25 cycles. So, by part A, utilization would be 10. If we keep the iCache small, it will 60/50p have a non-zero miss rate, m. We still fetch E instructions between mispredicts, but now of those E, m are 10 cycle, equals 20 slot, L1 misses. So the number of instruction slots to execute our instructions ist E, 120M, 221P, 1P10, 5200M, 40P, 120M, 40. Thus utilization 5200M, 40P will be 10. The larger cache will provide better utilization when Computer Network Assignment Help.com 3. I mentioned, in passing, that the return address stack predictor needs to be carefully repaired after a mispredict. Assume we are working with an architecture where it is easy to identify call and return instructions, as distinct from other branch instructions or non-branch instructions. Assume also that the BTB always hits and provides accurate information about the instruction being fetched. The return address stack, RAS, is a small structure that contains an array of, say, 8 addresses and a head pointer that points to one entry of the array. Each time we speculatively fetch a call instruction, we push the expected return point of the call, PC plus 4, onto the RAS. We do this by incrementing the head pointer, mod 8, and writing the return address at the corresponding RAS array location. Each time we speculatively fetch a return instruction, we predict that the next PC will be the PC currently pointed to by the head pointer. Then we decrement the head pointer, mod 8. First, assume that we don't do any repair of the RAS after a branch mispredict. Give a short sequence of instructions and events that will cause the RAS to get out of sync, i.e., mispredict all the return addresses currently listed in the RAS. Call a branch mispredict call B, bumps the RAS pointer, roll back to the branch, and now no matter what we do, every return will get its target from the RAS entry 1 above where it should be looking. 1010, or 5200M, 40P, 6050P, or P120M, 60. 50P, 5200M, 40P. Computer Network Assignment Help.com. B. Now, assume that we repair the state of the RAS as follows. With each branch instruction, we carry down the pipeline the value of the RAS head pointer, as it was when the branch was fetched. Much the same as we do with the global history. When a branch misprediction is detected, we reset the RAS head pointer to the position we carried with the mispredicted branch. Give a short sequence of instructions and events that will cause at least the next return address to be mispredicted, but not the contents of the rest of the stack. A. Call, head pointer equals 1, write value a plus 4 in RAS, 1, fetch branch that will mispredict, record head pointer equals 1, return, head pointer equals 0, B, call, head pointer equals 1, and we overwrite RAS, 1 equals B plus 4, roll back to the branch that mispredicted. This will restore the head pointer equals 1, but RAS, 1 equals B plus 4, not A plus 4. Thus the next return will try to jump to B plus 4 and end up mispredicted. 4. You are designing the register renaming circuit for the new OOPS Corporation processor. I guess OOPS must be an acronym for Out-of-Order Processing Systems. The OOPS is a 2-wide out-of-order superscalar. The OOPS ISA is much like MIPS or DLX. There are 32 architectural registers. Register 0 always contains the value 0. Instructions have at most 2 source operands and at most 1 destination operand. If an instruction does not have a destination operand, the decoder will tell the renamer that the instruction's